My name is Aurél Gábris, and I'm a researcher at the Faculty of Nuclear Sciences and Physical Engineering at the Czech Technical University in Prague, and as well at the Wigner Research Center for Physics in Budapest. And what I'm going to talk about today is a joint work with Pavlo Pishkin, who was at that time at the Wigner Institute as well, and since then he moved to Bilbao, I think, and where he's working, where he finished this this work with his present colleagues. And all right, I think I can use the pointer. Wow. Okay, so let me start with an overview. I will have a very brief introduction to what is goal research. I believe most of you are familiar, but nevertheless, I'm going to go through the main things to emphasize what we're looking at in our modified algorithm, which is going to be a non-unitary modification of the algorithm, and it's based on measurement and post-selection, and because of that, there are going to be different kinds of probabilities that we have to take into account. And what is interesting is that in this model, we were able to study the convergence and the scaling in a consistent way. And I'm also going to show you what could be an interesting use for this modified algorithm. And since it's not enough to press the mouse button, okay, so the first, I'm going to have two slides about Grover search, the original one by Grover and the continuous version, which actually our algorithm is based on. So you're probably all familiar. Grover search is the search in the unstructured database. The main thing is the oracle, which marks one of the elements in the search space. And the algorithm we know is that we start with an equal weight superposition, and then we iterate this part, and this rotates the initial vector in this two-dimensional space. Now this is for a simple visual understanding, and the probability that we measure the marked state will depend also in this sinusoidal fashion. So what we usually regard as the time it takes for the Grover's algorithm to finish is this first peak, and it means that we need to know the dynamics pretty well. We have to be able to measure the system just on time. Okay, if we do that any other time, it might not be so good. Nevertheless, this first peak appears much faster than in the classical case. So this is what Grover search is interesting, that it offers a quadratic speedup. Now this might be less familiar, but there is a continuous version of the search algorithm. This dates back to 1998 as well, from Paris and Wootton. And here the idea is that instead of using quantum gates and which perform this diffusion and an oracle that performs the marking as an operator, we have one Hamiltonian, and this Hamiltonian is the one that in turn generates the unitary dynamics. So this generation is given by this exponential e to the I h times t. So this t is the length of time that we're evolving. And the interesting part is the structure of this Hamiltonian, which consists of two terms. One is called the driving term. This is familiar. This is what includes this equal weight superposition. So it's in spirit very similar, uses the same kind of concepts as the standard Grover algorithm. And then we have a marking term. So this is a superposition that includes all basis states, whereas this W is meant to say that this is just one state. Okay, so if this one state appears in this Hamiltonian addition, this is what constitutes the marking of that particular state, and this is the W. Okay, so this has been studied already, and there are also some more ramifications to this algorithm. It's possible to derive an analytic formula for the probability of finding this marked node after time t steps. And what we notice here is that it's going to be the same sinusoidal oscillations as in the discrete time, except that this is in continuous time, and there happens to be a factor of 2 that appears here. Okay, but that's a constant factor. We're not really interested in that. So what are the issues with Grover search? I'm just going to mention one, and that's which I mentioned already very briefly. So that this position of the first peak, that might depend on the actual parameters which is used for the implementation. So if you have some errors which modify the position of the first peak, you don't know exactly at which time you would need to measure, and that's going to give you a lower probability that you obtain that particular result. And often this is not a problem, because maybe you obtain a result with a lower probability, but you can verify it no matter what. You just take the oracle, put it in, and see if it is the marked or not. And in that case, if you find that it's not the marked node, you can run your algorithm again, and then do it again, and then verify the next result. So this has also been studied in the context of this continuous time search algorithm in 2003, and there have been some interesting findings regarding this kind of like a critical point of the error that I didn't mention. Sorry. So there is another kind of error that can cause difficulties, and that's that if your oracle is not perfect, so maybe everything else works well, but you have an oracle that doesn't exactly behave the way you wanted. So instead of just having this term with, you remove all the dimensions there. So you just have that term without any factor. Instead of that, you might have some energy here that is due to some fluctuations. Okay, and then this can also have a negative effect on your search time. Okay, so this is also something known before, and this is all in the context of standard unitary evolution. So what we looked at, or the idea was Pavlov's idea to use something similar from his previous work, is to design a modification of this algorithm that would be based on measurements during the evolution. Okay, if we would just go and do and use the original protocol and make measurements during this time, that would destroy the superposition that we're using, and it would actually probably very strongly reduce the efficiency of this algorithm. So the modification that we considered is adding an ancilla to this Hamiltonian. And formally, this is how you can look at it. So these are still the original terms. So the first one is the ancilla, and the second system is the search space. And so if you look at this first term, this is essentially nothing else than just the Hamiltonian that does nothing on the first on the ancilla. And then there's an extra term which you can think of as a coupling between the ancilla and the search space. And this is the evolution that we're going to consider. Okay, so this is still going to be a unitary evolution, but what we're going to do is we only evolve stroboscopically for a certain time. Okay, so the notation is the following. So we assume that at some time n, the state of the ancilla, so the state of the joint system can be written as a product. Okay, we'll see why we can do that. Normally, this would be a very strong assumption, and we even kind of assume that we can parameterize the ancilla just by using these weird parameters, and then we evolve this h by some time delta t, and then we measure the ancilla. And we measure the ancilla in such a basis that it either projects onto this state that we have defined here or onto its orthogonal complement. What we do is that we only continue with the evolution if the measurement actually projects the ancilla onto this QN state. Okay, so if the projection jumps into the orthogonal complement, then we just avoid the algorithm and we assume that we're going to restart it. So there's a probability of success associated to this. So for every survival, I typed it, and this is a typo, it is meant to be a survival probability. So this probability of success will define that we're actually able to continue with the next iteration. So it's going to be probabilistic algorithm. But what we can read off easily here is that due to this projection, the joint state is going to be in this product form, and it's exactly going to be the product form that we have assumed here at the beginning. Okay, so if we started with a product state with some n which was equal to 0, which we can also define nicely, then all these assumptions will be consistent during the evolution. And before we proceed to the next step, we have to update this theta angle by some delta theta. Okay, and this is like, it's going to be very technical. I'm not sure that I'm going to go into the very technical details in this respect, but of course the analysis of the algorithm or the performance or the behavior of the algorithm will strongly depend on these two parameters, the delta theta and delta t. Okay, if you're interested in the details, the paper is on the archive and you can look it up. Okay, the main message is that because of this measurement, this is going to be a non-unitary evolution. Okay, so I mentioned that we're going to have two kinds of probabilities that we have to look at. So one, which I mentioned earlier, this is the survival probability. So what the survival probability is going to be is that if we want to do n iterations of the algorithm, and for each iteration, there's a p sub 1, and then the second one p sub 2. So for each iteration, there's a probability that we succeed. The overall probability, which we call the survival probability after that step, is going to be a product of these guys. And these probabilities have this interesting property that after some initial transient behavior, they converge to 1. So what it means is that when we start the algorithm, there's a fairly large chance that we fail and we have to restart it. But once we're past a certain time, it's actually, we can continue without any additional cost of so the cost of continuing in terms of this post-selection is approaching 0. Okay, so from here on, our algorithm essentially behaves as if it was a unitary algorithm, because we don't have this extra cost that comes from the post-selection. And this is actually something which is known in quantum physics as the Zeno effect, or something similar. That by measuring this by observing the system, we're actually forcing it into a certain state, and then once it has been forced into that state, every subsequent measurement is going to reveal that this particular system is in this state. Okay, here we're not measuring the entire evolution; we're only measuring the ancilla. So what happens if we try to characterize what happens to the rest of the system, or the third space? So for this, we will, as usual, we regard a probability. So this probability is going to be the probability that we measure the marked state into the output after n iterations. This is the formula that it gives. We call it the target fidelity, so that we try to not mix up things, probabilities and fidelities, although of course this is also going to show up as a probability in the end. And what we see is that even in the search space, we see similar behavior. So we have some transient in the beginning, and after some transient, this target fidelity saturates and approaches one. Okay, so it means that if we evolve the system for some time, after some time, it's guaranteed that that the register is going to be in the marked state. Okay, so this is a nice behavior, and it's something that we have observed numerically, and I mean numerics is nice, but it has like limitations, right? You're not completely sure when the saturation would be reached, or when we see that there's a slight discrepancy between this so the dashed line is what you would get from the continuous Grover algorithm. So this is for reference. Okay, so it would be interesting to compare the continuous Grover with this non-unitary algorithm. And numeric doesn't really allow you to like say what will happen to this gap. Is it going to behave nicely, or is somehow it's going to take a very long time if we do large search spaces and so on. And the nice thing is that what Pavlo was able to figure out is that he found a way to analytically treat, or at least in some way find a very efficiently computable analytic upper bound to these efficiencies. And in order for me to explain what the idea was behind is, let me formulate this evolution now in a different way. So what I would like to concentrate here is the evolution only of the search space. Okay, so the ancilla is not here. We start with the equal weight superposition, and there is some map that maps the initial state after n iterations into the state of the register, and this would be given by a product. This is an ordered product, so it's a product of operators that is given by this formula. So this operator is the unitary on the entire space, and then we project onto the initial and the output. So we get another operator, which is a projection of the original unitary. And of course, this may not be a unitary operator because of the projection.
Aurél,
may not be an operator.
1 minute. You have 1 minute. Please try to.
Oh, I didn't realize it was. I don't have. Somehow I don't see the time on this particular one. Okay, so in this approximation, what we have been able to do is we still write it in this particular form where this V is generated by some operator exponentiated, and of course this is going to be a non-Hermitian thing, but nevertheless it is possible to study analytically. And what we have found is that you can rescale this Hamiltonian. You can't do it arbitrarily, so you can rescale if you have it for some size n1, you can rescale it not to an arbitrary n2, but it's easy to find one which is larger than that, and then there is a certain relation between these parameters that I have mentioned about, and essentially what it tells us that this rescaling comes up in this very simple form. So the time is rescaled by the ratio of these two guys and these two guys, and of course this doesn't work for an arbitrary n2, but we can always use it to establish an upper bound whenever we have some certain r, and so how to find it is it's a numerical procedure, but it's a very straightforward one. Basically uses a closed formula. We didn't actually check rigorously, or we don't have like exact result what is the spacing between these two ends, but they seem to be sufficiently close to each other. So this is a very, very nicely usable upper bound to estimate. So
okay, Aurél, just 1 or 2 sentences because time is finished.
There's only going to be one more comment. So when when we think that there would be an interesting use case for this algorithm is that in the case when you don't have a direct access to the Oracle Hamiltonian. So what I mentioned is that if you don't have perfect success, then you have to verify your result. But if you have no way to verify, you have to use some alternative technique. And this could be a way to do that, because due to the Zeno effect, if you're able to conclude with your algorithm, you always have nearly unit probability that you're going to end up in the marked state. So with that, I would like to thank you for your attention.
Thank you, Aurél.